I have been struggling in Mathematica to do the following type of problem. Imagine you have a complicated function, and you want to find the roots of that function. So right now it's a numeric function, or sorry, an analytical function. One could imagine having, like an interpolation function or something that you really want to find where the roots are. So we can see the roots. The human eye is pretty good at seeing, oh, they're here, 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 and here. So there's 1, 2, 3, 4, 5, 6, 7 roots. It's certainly between -2 and 2. Here's the problem I have. If you use find root in Mathematica, it, here I'm saying start at 0, so it starts at 0. And look what root it found. It found the 1.4 root, which I believe is actually this one. So it actually skipped 1, 2, 3 roots before it found the one that it was looking for. Then I thought, well, maybe it's because I'm starting at 0. What happens if I start at -4? So I start way to the left. If you start at -4, the root that it finds is -0.6, which is this one. So it actually still skips a root. So, of course you can put this in an iterative fashion where you have find roots start at lots of different locations. You can also give it a little bit more detail in where you want it to look. But what I've been playing with is a new way to do it. So here's my new idea. If I do an NDSolve command, NDSolve has this cool method called event locator. And what event locator does is, as you're walking along of the NDSolve, it can evaluate whatever you want to look for in the event. And if this event ever equals 0, then it will do lots of things. It can stop the simulation, or you can set the event action to save it. So what I did was NDSolve, look at this simple differential equation I'm solving, that the velocity of a particle is equal to 1, and I'm starting at -4. So we all know what the solution of this is. It's just going to walk forward at a constant speed all the way across my range of interest. So I have it go out to 8, so it's going to go from -4 to 4. But what I have it check is the event of my function at that location. And I say if this ever equals 0, then store it. That's what the so command does, the reap and the so does. If I didn't do this max step size, it doesn't work, because this is such a simple differential equation. If you let it do its own step size, it immediately realizes how boring and easy this is, and it just jumps to the end, and it actually doesn't literally walk through the entire range. But I set my step size to be relatively small, 1/100th of a point here. And look what happens. The roots give me 1, 2, 3, 4, 5, 6, 7. Watch how fast it runs. So let me put a timing command on here. It runs in 1/100th of a second or so, and I get all 7 roots. Now you might ask, well, how accurate are those roots? Well, I can ask for the function at those roots, and you can see that it's highly accurate. So it's not that Mathematica is simply stepping through at this rate. It's actually, once it gets close to an event I care about, it seems to be using its internal algorithms to really nail down where exactly that step is. I think, I haven't dug into this in detail yet. I think it might simply be doing an interpolation between these points, and maybe my function is smooth enough. But watch what happens if I move my roots over by 0.0000, or sorry, 3 zeros and a 1. So if I move all of these roots over, I change essentially this digit. Well, clearly the function is far away from being true 0. So I would have to say that whenever I see roots being this accurate, I'm pretty pleased. Now what happens if I change the step size by 2 orders of magnitude? First of all, it reaches 1,000 points, and so it doesn't even quite get as far as I want it to go. I could do max steps infinity. Let me try that. And you can see it took a little bit longer, almost a full second, but I have all my 7 roots. I'm just going to reevaluate this command just underneath it, so we can see if there's any differences. So first of all, it nailed this one a little bit better. This one is to the same accuracy. This one's to the, well, this is about almost an order of magnitude better. This one is still, but still, I think that we'd be pretty pleased with these roots. Let me also do roots full form. So you can see that it's actually getting it out quite a number of digits here, and it's certainly not limiting itself to the step size here. So I'm pretty pleased with this. It seems like the fastest way to get the roots of something. You could also, by the way, find out where the derivatives are 0. I think that all I'd have to do is put a prime right here. Let's see if that works. Yep, and now we have all the locations where the derivatives are 0. So this is kind of a slick way to use NDSolve to find events of interest in a function.